Vector memory access. If you're working with modern processors, maybe in AI or high-performance computing, this can be a real headache.
Oh, absolutely. It's often the critical bottleneck, just moving data around efficiently.
Especially when it's not just a simple, neat block of data, right? Those trickier patterns are the real challenge.
Yeah, exactly. And today, we're going to take a deep dive into a paper that tackles exactly this for RISC-V vector processors.
Right.
It's called Efficient Architecture for RISC-V Vector Memory Access. Comes from researchers at Tsinghua University and Intel Labs, China.
Interesting mix. So let's frame the core problem they're going after. Vector processors, great for parallel data crunching, SAMD stuff, but they kind of stumble when it comes to memory accesses that aren't just straightforward. Const-stride patterns, segment patterns, those seem to be the main culprits.
That's right. And the typical solutions, they often involve pretty heavy hardware. Big, complex crossbars routing individual bytes or needing large temporary buffers just to rearrange data.
Which sounds expensive. In terms of chip area, power.
Definitely. And performance can take a hit, too. It's just not as clean as handling sequential data. There's this inherent inefficiency.
So what's their big idea? This paper introduces something called Earth?
Yep, Earth. And the core concept is using clever shifting-based optimizations, trying to get away from those costly crossbars and big buffers.
Okay, shifting. Sounds intriguing. So for everyone needing the quick version, the TLDR for this deep dive, Earth uses some new bits of hardware, DROM, LSDO, and RCVRF, specifically built to handle those tough, strided and segment accesses much better.
And the results they got, well, they evaluated it on an FPGA and saw some really significant speedups. Think 4x to 8x faster on workloads that are heavy on those stride patterns.
Wow, 4x to 8x is huge. What about cost?
That's the other part. They actually saw hardware area reduction for the bigger configurations up to about 9.11% compared to a standard design like Saturn. And power savings, too, up to 41.6%.
Okay, so potentially faster, smaller, and less power hungry.
For certain configurations and workloads, yes. And importantly, they managed this while staying fully compatible with RISC-V vector ISA, especially for those segment operations. That's the headline, really. Big efficiency gains where they're most needed.
Right, let's unpack this more. Why is vector memory access so difficult? Vector processors themselves are great, right?
Yeah.
Finance, AI, signal processing, one instruction, lots of data.
Exactly. SIMD is powerful. And the RISC-V vector extension, or RVV, it's quite flexible. Variable vector lengths, which developers like.
But flexibility often means hardware complexity, doesn't it?
It can, yeah. The real difficulty is bridging the gap between how memory is usually laid out nice and sequential and the potentially scattered pattern the vector instruction actually needs the data in.
So the RVV standard defines different ways data can be accessed.
There are a few key patterns. The simplest is unit stride.
Easy mode, just grab a contiguous block, done.
Right. Then you have strided access. Here, there's a constant gap, a stride, between the elements you want. Think accessing columns in a matrix stored row-wise, or pulling specific fields from an array of structures.
That sounds really common.
It is, very common, but much harder to make efficient than unit stride.
Okay, what else?
There's indexed access, scatter-gather, basically.
Yeah.
You have another vector that holds the memory addresses for each individual element you want. Super flexible.
But sounds complex.
Yeah.
And probably slow.
Often the most complex, yeah.
Oh.
And maybe less frequent depending on the workload. Finally, there's segment access.
Segment.
This is for things like array of structures, data layouts. You want to load or store elements belonging to the same logical segment, but spread across multiple vector registers. The tricky part is it needs this kind of row-column transposition.
Like flipping the data organization between memory and the registers.
Exactly. Turning sequential memory data into this structured form across registers or going the other way. That's tough.
Okay, so let's zero in on the specific bottlenecks the paper points out for strided and segment patterns. What makes them slow or expensive?
For strided access, the problem is getting data elements that aren't next to each other in memory, but might still be within the same cache line. A naive design might just issue, say, 8 separate memory requests, even if all 8 bytes are in the same 64-byte cache line.
Which is incredibly wasteful, right? Redundant fetches.
Hugely wasteful. Or, to avoid that, designs use these complex, power-hungry crossbar networks. They fetch the whole cache line, and then the crossbar picks out the specific bytes needed and routes them to the right slots in the vector register.
Right, the paper had that example, loading 32 bytes with a 2-byte stride. Could trigger 32 cache accesses, even if it's just one cache line picking up byte 0, byte 2, byte 4. that need some fancy plumbing.
Fancy, expensive plumbing that adds latency, especially as vector lengths get longer. It's like trying to grab specific colored marbles off a fast conveyor belt, hard to do efficiently all at once without a clever sorter.
Good analogy. Okay, what about segment operations? What's the killer there?
The transposition, that's the main issue. Designs either handle it element by element, which is painfully slow, just serializing the whole thing.
Yeah, that defeats the purpose of vectors.
Right. Or they use these really large, dedicated transposition buffers, load the data in, shuffle it around in the buffer, then write it back to the registers correctly organized.
But the paper mentioned segment instructions aren't even used that often.
Exactly. So you have these potentially huge buffers. The paper talks about needing dual buffers, each capable of holding data for like 8 full vector registers, just sitting there taking up valuable chip space and burning static power most of the time. It seems questionable.
Okay, that definitely paints a picture of the problem. So Earth comes in with this shifting-based approach. How does that work?
Instead of relying on those big external buffers or massive crossbars for the heavy lifting of data reorganization, the core idea is to build specialized shift networks and, crucially, a redesigned register file directly into the vector load store unit's path.
Integrating the reorganization logic more tightly.
Precisely. And they introduce 3 main building blocks for this.
DROM, LSDO, RCVRF. Let's break those down.
Okay, first is the Data Reorganization Module, or DROM. Think of this as the central engine for gather and scatter operations. It's pretty versatile.
Then there's the Load Store Data Organization Module, LSDO.
Right. LSDO works closely with DROM, but it's specifically tailored to optimize those strided accesses, enabling the coalescing we talked about.
And finally, RCVRF.
That's the row column accessible vector register file. This is the key piece for handling segment operations without needing those dedicated segment buffers.
Okay, so DROM and LSDO are part of the load store unit pipeline, and RCVRF is actually a new type of register file.
Exactly. You can see in their diagrams how it fits into a typical RCV vector unit design, like the Saturn baseline they compare against.
Let's dive into DROM first, the central shuffler.
Yeah, you can think of it like that. It's built around these specialized shift networks. There's a gather shift network, GSN, for loads taking data from memory and gathering it, and a scatter shift network, SSN, for stores taking data from registers and scattering it out.
And they work in opposite directions.
Sort of top-down versus bottom-up flow. These networks are constructed in layers, and each layer can perform shifts by powers of 2. This structure lets them efficiently move data elements from potentially scattered input positions to the required target positions in the vector register or memory stream.
Sounds complex, but efficient. They mentioned something about conflict-free.
Ah, yes, that's important. They mathematically prove that because of how the shifts are designed, preserving order and separation, the paths for different data elements moving through the network simultaneously won't collide or interfere.
So one pass is enough. No complex routing or retries needed.
Essentially, yes. It guarantees efficient routing. But the network needs to know how much to shift each piece of data. That's where the Shift Count Generation Module, or SCG, comes in.
Okay, so SCG calculates the shift distances.
Exactly. For any given access pattern, like a strided load, the SCG figures out precisely how far each individual byte or element needs to be shifted by the GSN or SSN to land in its correct final position.
So for that strided load example, we would calculate, okay, this byte from memory position 5 needs to shift X places to become the first element in the register. This byte from position 7 needs to shift Y places to become the second element, and so on.
You got it. It's the brain that directs the shifting muscles of DROM based on the stride, element size, and where the data is coming from or going to.
So DROM uses the SCG's calculations to configure its networks for either gathering loads or scattering stores. Makes sense. Now, how does LSDO fit in? You said it uses DROM for strided access and coalescing.
Right. LSDO acts as the main interface and organizer for strided patterns. It sits in the pipeline and includes things like a reverser just in case the stride is negative, and it contains the DROM module itself.
So the flow for a strided load would be data comes back from the cache or memory.
It goes into the LSDO module. If it's a strided access, LSDO directs it into its internal DROM. DROM, using the shift counts from SCG, then does its magic taking those scattered bytes within the fetched memory chunk and efficiently rearranging them into the nice contiguous block needed for the vector register.
Ah, okay. So that's how they achieve coalescing, by processing potentially multiple strided elements that fall within one cache line using just that single memory fetch, and then using DROM inside LSDO to sort them out afterward.
Exactly. It avoids the multiple redundant requests and avoids needing a massive general-purpose crossbar to do the byte picking. It's a specialized, efficient pipeline for strided data.
Very clever. Okay, let's tackle the RCVRF, the register file that handles segments without buffers. This sounded like the most radical part.
It is pretty novel. The RCVRF row-column accessible vector register file is designed so you can access it in two ways. The standard way is row-wise, meaning you access elements within one single vector register, just like a normal VRF.
Okay, standard access?
But it also supports a column-wise access mode. This lets you access the same element position across multiple different vector registers simultaneously.
Whoa! What does that work? You need special wiring?
It's about how the data is organized within the register file's physical banks. They partition the register file into multiple banks, typically 8, because segment operations can involve up to 8 registers working together.
Right, standard banking.
But here's the trick. They map the data elements not just within a bank, but across the banks and rows in a specific patterned way, almost like a diagonal mapping.
Diagonal mapping.
Yeah. The goal is to ensure that elements that logically belong together in a column for a segment operation, like element 1 from register V0, element 1 from register V1, element 1 from V2, and so on, are actually stored in different physical banks.
Ah, so you can access them all in parallel by hitting the different banks simultaneously.
Precisely. It's like organizing your bookshelf, so all the chapter 1s from different books are on different shelves, allowing you to grab them all at once if needed.
Okay, that makes sense. So standard row access works normally, but for segment operations, which need that column data.
You use the column-wise access mechanism. It reads from the necessary banks in parallel, getting the column data out. It might need a quick alignment, and then guess what DROM gets used again?
DROM again. How?
In this case, DROM performs a final reorganization using a constant stride determined by the element size and how many registers are in the segment, the EMOL value. It takes the data gathered from the columns and puts it into the final contiguous block needed by the processor or for sending to memory.
So DROM is really the workhorse here, used for both strided reorganizing and this final segment column cleanup.
Very much so. But the real win with RCVRF is that because you can directly access the data in this column format, you completely eliminate the need for that huge, separate segment transposition buffer.
Right, no load into buffer, rearrange, right back from buffer cycle.
Exactly. If you compare the timelines, the paper shows element by element segment processing is just slow sequential access. The buffer approach has a distinct load phase, then a buffer to register write back phase. Earth, with RCVRF, essentially does the load directly into the register file using the column-wise access, cutting out that buffer step and the hardware that goes with it.
Much more direct. Okay, so we have the pieces. Briefly, how do the flows look for different access types in Earth?
Sure. For strided loads, memory interface splits requests if needed, manages queues, reorders responses. Data hits LSDO, DROM inside, gathers and aligns it. Then it's written row-wise into the RCVRF. Stores are the reverse, read row-wise from RCVRF. LSDO uses DROM to scatter align, then out to memory.
Standard enough, but with the LSDO magic. Segments.
For segments, they stick to the standard RVV segment-wise approach for compatibility. Requests are split by segment, coalesced within memory lines. Data comes back, LSDO aligns it slightly, and then it's written column-wise into the RCVRF using that special mode we discussed.
On simple stuff like unit stride or indexed.
They mostly follow the conventional path, similar to the Saturn baseline they use for comparison, but the data still flows through LSDO for final byte alignment before the standard row-wise write into RCVRF.
Got it. So LSDO handles the final alignment, even for the simple cases.
Yeah.
Okay, the architecture sounds plausible. Did it work? What did the evaluation show?
They did a pretty thorough evaluation, implemented Earth on an Intel Stratix 10 FPGA, hooked it up to a RISC-V core, and ran a mix of benchmarks. Standard stuff like OpenBlay, RVV bench from the community, plus some custom benchmarks they wrote specifically to hammer strided access patterns.
Smart. Stress test the key area.
Right.
And they measured performance, area, power.
Yep, the whole trifecta. Performance-wise, the big story was definitely strided access.
Those 4x8x numbers.
Those were on specific stride-heavy workloads. On their custom stride-intensive benchmarks, they saw speedups hitting up to 14x compared to the Saturn-like baseline design without Earth's optimizations.
14. Okay, that's impressive.
Yeah, the average improvements were also really solid, around 3.8x to 4.4x, depending on the exact Earth configuration. And importantly, The gains were biggest with smaller strides, and when the code had a higher intensity of stride operations, which are very realistic scenarios.
So it helps most where the pain is greatest. What about other patterns?
For unit stride and segment patterns, performance was generally comparable to the Saturn baseline, which is actually a win for segments, remember. They got the same speed without needing the big, costly segment buffers.
Good point. Comparable speed plus area power savings is a win. Did they compare to anything else?
They did a brief comparison against results from actual silicon, the SpaceMet X60 processor. Earth generally performed better, especially on strided stuff, though interestingly, the X60 was notably stronger on indexed scatter-gather accesses.
Ah, so maybe room for improvement there on Earth.
Potentially, yeah. The paper acknowledges the X60 likely uses specialized hardware like lookup tables for index, which Earth doesn't currently focus on.
Okay, performance sounds good, especially for strides. What about the hardware costs? Area and power.
Right, area. The RCVRF register file itself is a bit bigger than a standard one due to the extra access logic, about 15–20% larger, roughly.
Okay, a cost there.
But they saved a huge amount of area in the load store unit by ditching the segment buffers entirely. We're talking savings of 37% up to nearly 65% in the LSU area, depending on the configuration.
So a trade-off. What was the net result? Overall ship area.
For their smaller econfig, the overall area was slightly higher by about 0.6%. But for the larger pconfig, where Saturn's segment buffer really balloons in size, Earth came out significantly smaller, a 9.11% reduction in total area.
Wow, so for more complex cores, it's actually smaller. That's a big deal.
It is. It shows the benefit of removing those buffer scales well.
And power. You mentioned savings earlier.
Yes, substantial power reductions overall, around 29% for the econfig and up to 41.6% for the pconfig compared to baseline.
And the source of those savings.
Two main things. First, the strided access coalescing dramatically cuts down on memory traffic. Fewer redundant fetches means less activity in the memory interface, caches, buses. That saves dynamic power.
Makes sense.
Second, and this is huge, just removing those big dedicated segment buffers eliminates all their associated power draw, both dynamic when they're used and static when they're idle.
Even though the new shifting logic in DROM must use some power.
It does add some switching power, yes, but the savings from reduced memory traffic and eliminating the buffers far outweigh that cost. The net effect is a really significant power saving.
Okay, so wrapping it all up, Earth seems like a really compelling approach. It tackles these known, difficult vector memory access patterns, strided and segment, using these novel shifting techniques, DROM, LSDO, RCVRF.
Yeah, it seems they successfully addressed those key bottlenecks. The results show strong performance gains, especially on the critical strided workloads, plus potentially significant area savings on larger designs, and really substantial power efficiency improvements.
It definitely sounds like a valuable design direction for future RISC-V vector processors, making them more efficient, more practical.
Agreed. It provides a path to better data flow.
Now, here's something interesting the paper just touches on. They mentioned this shifting-based architecture is inherently scalable. You could potentially have multiple load store units maybe working in parallel, GPU stuff.
That opens up possibilities.
So here's the thought to leave you with. If these shifting principles work well within a single LSU, what happens if you scale them up? Apply similar ideas across multiple LSUs working together. Could that unlock even more memory-level parallelism, maybe tackling those truly massive, often fragmented data challenges we see growing in AI and other fields?
That's a great question. How does this fine-grained data manipulation scale to the system level? Definitely something to chew on.
Absolutely. Well, that's been our deep dive into the Earth architecture paper. Hope you found it useful.
Thanks for joining us.
We'll catch you on the next one.